Hello and welcome. This will be our last video of this course, and in this video we'll be discussing kind of the rest of the multiple regression concepts and how we can implement them in R. Specifically, we'll be discussing how we can implement coding of categorical variables in R, how we can do polynomials in R, how we can do interactions, as well as how we can check assumptions, including our new assumption, and how we can implement standardized regression coefficients. So let's go on and get started. To start, I'm just going to go on and clear out the variables that I have here and load up this Deuterium library so I have access to the data sets and functions within it. We'll just be using the data sets here. Now, we're going to be talking about types of terms to start with, and I'm going to start with binary variables. And I'm going to be using a few different data sets to exemplify the different approaches we would take. And I'll be doing this in R just by pulling the different data sets from Deuterium. So these are already loaded up, but don't be confused when I go back and forth between data sets, between examples. I'm doing this because the different examples may have, one example might have a group with category with 2 levels in it, and one might have a category with 3 levels in it. So that's the idea here. So we're going to start with the depression data set, one of the first ones here. And I can see that it has this treatment variable. This is going to be my categorical variable that I'm using. The table command, I'm going to do depression, and I'm going to pull the treatment category from depression, counts up how many individuals in the data set fall within the different categories. So table creates what's called a contingency table, and we use this back in our chi-squared analysis. Here I can see I have 12 people in the control group and 12 people in the treated group, and I can also see that the names of my groups are CTR and treated. Now, to create my model, I'll call it bin mod 1, and we're going to be creating a fair amount of models in this lecture video. I'm going to look at the values of people in time 3 based on the treatment. And I'll note, in this case, I'm just passing in the treatment variable. I'm not doing anything with it. So I'm going to let R take care of coding the categorical variable using R's default coding scheme. So that's what we're going to talk about in this course, is kind of letting R do that. We're not going to talk about building our own custom things. If you wanted to, you could use if statements to define a new binary treatment variable and make it 0 and 1. In our case, we're just going to use R's default value because well, honestly, because it works. We'll just run with that. All right, so let's do summary of bin mod, and I want to show you what's going on here. First of all, when I look at my results, you'll see I have my intercept, as is typical of the regression model in R, but I have this treatment treated. Essentially what this says is in R, it'll give the name of the categorical variable and then the level that it used to make that particular dummy coded variable. So in this case, the dummy coded variable is treated, which by implication means our reference category is the control group. And so this is why I'm pulling this up. It's really nice that in R, I don't necessarily have to make dummy coded variables, but I do have to find, well, which one is the reference category. So there's a few fancier things we can do with that. And if you're interested, I highly suggest checking out our course on how we can, do a little bit more with programming and statistics. Not super complicated, but we can essentially set the reference category with another 5 minutes on a video. We're not going to worry about doing that here. In this case, we are just going to talk about, hey, based on the output, I can tell which one is the reference category. So this is comparing treated to the reference category. Looking at this group, I can see that the score at time 0 for the treated group is 90 points on average, lower than the score for individuals not in the treated group. You can see, so that's the interpretation of my parameter estimate for treated. This is 90 points lower than the reference group. And this is statistically significant. That is, there's a significant difference between the treated group and the not treated group. I can also say, remember, this is a binary variable. It's 0 when the person is in the control group. So this 197.17, assuming an equal sample size and all the rest, represents that on average, people in the control group scored 197, and people in the treatment group scored 90 points less than that number. Real quick, and actually I didn't have this for my case, but I'm just going to do it anyway. You can use the function aggregate with data in this long format here to calculate quickly the means for people in each group or the variances or whatever. So I'll do T3, that's the variable I want to calculate the means for, and then treatment. And again, this isn't strictly necessary, but we'll do it anyway. Depression. And we'll give it the function that I want it to calculate is the mean. And I'm doing this to simply indicate that the average value for the control group is 97.1667, which is exactly what this intercept interpretation is. The average value for the treatment group is 106, which if I do 97 minus 106, with a little bit of luck, 197.1667 minus 106. And I didn't test this out beforehand, so I hope this works. 667 gives me 90.5. So the treatment group is 90.5 less than the control group, and that's my interpretation here. And in general, I'm not going to do this for every one. I'm just kind of thankful it worked out for that one. I'm not going to do this for every one. Remember, if the data sets aren't balanced, that is the same sample size in each group, that may or may not work. Also, if you have other independent variables in this, that may or may not work. Depending on a lot of things. But in any case, for this, looking at that particular calculation, this is kind of what we mean when we say when we're talking about the parameter estimate for binary dummy coded variable. The interpretation, broadly speaking, relates and is the same when we deal with multiple binary coded variables. So if I have like a polynomous categorical variable, remember more than just two categories, the interpretation is largely the same. Okay, so I've got 3 dummy coded variables, all being compared to the reference. Again, the intercept referring to the reference, all of the independent variables equal to 0. And then the 3 variables are comparing this particular category to the reference category, a negative 90 indicating that this variable is 90 points below the reference category, and the p-value testing is it significantly below the reference category. One more thing that we quickly mentioned is that this was analogous to a t-test. So we ran the t-test command. Gosh, it feels like years ago, doesn't it? So I'll just run this T3 squiggle treatment. Data equals depression. I can't remember if when we introduced t-test, we talked about how to run it in long form, but this is the notation for running the t-test in long form. Let's see here. We have the means of the groups. I have my t-value matching up exactly and my p-value matching up almost exactly. The difference here is going to be my degrees of freedom. Remember my degrees of freedom here, I'm using 22 degrees of freedom. Down here, I'm using my Satterwhite approximation degrees of freedom. So that's the only distinction going on here. Again, my test statistic is the exact same. It looks like the p-value is a little different. And don't worry about the negative versus positive. Remember, that's which group comes first. So in this case, we're doing treatment minus control, treatment as relates to control. In this case, we're doing control minus treatment because that's just how R put that in this particular case. So don't stress about the negative versus positive. That's just which one came first. We're looking at the magnitude of the t-value and, of course, the p-value. Again, degrees of freedom in a regression, a little bit different than degrees of freedom in a t-test, but we could rerun this. Note that this uses DFE. Cool deal. All right. Actually, I wonder if we did the correction equals false, or what would this, this would be var.equals, equal variance. Do we have that on here? Yeah, I won't screw around with it too much. Y'all don't need that. The degrees of freedom are what's different. That's what's changing this up. And actually, we could just manually calculate with a different degrees of freedom and test that, but we won't worry about it. Alrighty, so let's see what's special about running this with regression. That is, why would I use the regression as opposed to a t-test? And that's a good question. In this case, I'd probably use the regression instead of the t-test because, again, regression lets me account for more variables than just the t variable that makes my groups. So the t-test is on a single categorical variable with two categories, but regression allows me to include more variables in my analysis. For instance, this says treatment is significantly different, but I'm just looking at the post scores, that is at the end of the treatment procedure. Maybe I'm interested in finding, are the post scores different after between treatment and control after accounting for the pre-score? So maybe more depressed people came in one group, the control group, and less depressed people came in the treatment group. And so I want to look at not just is treatment and control different on average, but are treatment and control different after accounting for the fact that different people may have come in different groups. Now, I'll say with this particular structure of question, you do want to be careful because in this particular structure of question, when we're doing these types of controls, it is most formally defined when we have random experimentation. So this increases statistical power, but if there's systematic difference, depending on where that systematic difference comes from, statistical control of that systematic difference isn't appropriate. With that said, again, don't stress too much about that. Just acknowledge how cool it is that now I get to say something to the order of, I see that the accounting for the previous variable ahead of time, the previous test score on depression is not statistically significantly related after accounting for which group the person's coming in. That's very fascinating to me, that the pre-depression score is not related to the post-depression score, the at time equals 3. That is very, very fascinating. That's a very interesting finding. In fact, if this were research, I'd probably look more into that because that's such an interesting finding. It goes so against my gut. I would normally think, if you come in depressed, you probably leave depressed. If you come in not depressed, you probably leave not depressed. And this is saying that there's no relationship. If you come in depressed or not depressed, I can't tell you if you're going to come out depressed or not depressed because they're unrelated to one another. In any case, our interpretation for the effectiveness of the treatment now changes. Now I can say the treatment is statistically significantly lower scores than the control group after accounting for the individual's pre-test scores. And that's a pretty cool interpretation, and that's a pretty cool addition to our interpretation. Again, we can do that with regression, but I can't do that with a t-test. There's no place to add on the t-test in that particular case. So it's a nice thing about regression, and one reason I like regression. All right, polytomous variables. Polytomous, maybe? I don't know how to spell it. Don't assume that that's the correct spelling. Maybe it is. Maybe I got lucky. I don't know. All right. Polytomous variables. So in this case, I'm not going to use the depression data set. I'm going to use the anxiety data set. Way more fun. Head, again, just displaying the first 6 values. I'll do a table of the group variable from anxiety. So I'll tell it the anxiety data set, $, which means just pull off the column. And then I pull off the group column. Oops, I don't know what I hit there, but let's not do that. And I have 3 groups now, and this is why we're switching data sets. Previously, my treatment was just 2 groups. That was the binary variable. Now we're talking about 3 groups, group 1, group 2, and group 3. Essentially, what I'm going to do is echo the previous analysis that we kind of did. And now we're going to look at a data set with 3 groups. So I'll call this cat mod for categorical variable. I guess, a binary variable is still a categorical variable. But I'll call it cat mod and just know what I'm talking about. Again, looking at the head of my data set, I see that we have 3 time points, but now the first time point is time 1, not time 0. And so I'll write T3 squiggle group and data equals anxiety. Awesome. So I can look at a summary here. And again, think about what you're expecting. I have 3 groups, and remember my process for creating dummy coded variables and including them in regression with 3 groups. The process is I pick a reference group. R usually uses the first one, but whatever. I pick a reference group. And then I make categorical variables for the other levels of the variable out of the reference group. So if R uses the first one as a reference group, I'm expecting categorical variables for group 2 and group 3. The parameter estimates for these are going to compare group 2 to group 1 and group 3 to group 1, respectively. So that's what I'm expecting to see is categorical variable listings for the dummy coded variables for group 2 and group 3. And by process of elimination, that means that group 1 is in fact the reference category here. Now, I would never assume that. I would always double check that in my results, and I can see that. Here, comparing group 2 to group 1, I see that there's not quite enough evidence for a statistically significant difference at alpha equals 0.05, but R notes that there is enough evidence at alpha equals 0.10. You set alpha at the beginning of the problem, so we would just have that preset. Actually, you set it at the beginning of the problem to keep you from looking at this thinking, but I want group 2 to be different, and then changing your alpha on the fly. That would be bad practice. Here we set alpha at the beginning, typically 0.05, so this would be considered not significant. And then group 3 is being compared to the reference group, group 1. So the comparison between group 3 and group 1 indicates a statistically significant difference there. All right, so I mentioned earlier when we have a categorical variable that I include and I let R break down on its own, if I do the ANOVA table, it'll evaluate the joint contribution of the entire categorical variable simultaneously. Now, this is true when I have other independent variables in the model too. Remember, by default, R presented in the ANOVA table each of the independent variables separately. But with categorical variables, it'll join up all of the binary variables and present that categorical variable as its own row. So you can kind of do a test of if that categorical variable as a whole is contributing. In this case, in my test of this categorical variable in general, this categorical variable is contributing, and you can kind of see that, which part of it's contributing. Well, group 3 is different than group 1. Note, again, this doesn't compare group 2 and group 3. We only do comparisons to the reference category when we create dummy coded variables for a polynomous item. If I wanted to do a comparison between group 1 or group 2 and group 3, I'd have to rerun the model, set group 2 or even group 3 as the reference category, and then the other one would now be comparing to that group. All right, so let's compare this to what we did for our ANOVA. Our ANOVA was AOV. We gave it the outcome variable, T3 in this case. We gave it the independent variable and the data set, data equals anxiety, and you'll see that this gives essentially an identical report on sum of squares, mean squares, the F value, the P value. All of these things are identical to one another. That is to say, running the categorical variable in regression, it does have different output in the regression output, but if you do an ANOVA table output, the ANOVA table output is going to match identically to if we just ran an ANOVA. The additional benefit in the regression model, not only do I get to look at the individual pairwise comparisons, which you could do with ANOVA. Remember, we could do the post hoc test with ANOVA, but with the categorical variable in the multiple linear regression, I can add other independent variables if I want to. So I could add on the pre-value at T1. I could add on other information if I had other information about the person's demographics, etc. And that would let me interpret the group effectiveness or the group differences after accounting for all of that other information. And that's just not possible with our ANOVA. I shouldn't say not possible. Again, all of these are mathematically kind of the same, and we're demonstrating that they're mathematically the same. But under our ANOVA, as we discussed it in the lecture, it doesn't really have room to add continuous variables, while multiple linear regression has room to have both continuous and categorical variables. Again, that's the big benefit of it. All right. So from polynomous terms, now let's go to another word, polynomial terms. So remember, polynomials like squaring values, and I'll say there's two ways to do this. I'm going to do this by hand, and I'll do this both ways. Actually, I wasn't sure that I was going to do this both ways, but I'll do this both ways. We'll use the CARS data set for this one. And in cars, we have the speed of the car and the distance that it takes the car to stop. So in this particular case, maybe I'll look at a plot of the car's speed. That'll be my x-axis value. I think the distance it takes to stop depends on speed. That is, I think speed is the independent variable and distance is the outcome or the dependent variable. So speed is my x-axis, the independent variable. The car's $distance it takes to stop is the dependent variable. And this is what that looks like. Now I might look at this and say, you know, a line looks pretty reasonable here, but I also could look at this and say, you know, maybe there's a bit of an upward curve here. So I want to just run this. I want to just test if there is a curvilinear relationship. And again, this is kind of an analytic approach. I look at data, I'm trying to explore this, and I run my tests to test things. I have a thought. I'm kind of curious about it. I'm not tied to it. I'm just going to test it and see. I don't have to make an assumption as to if it's there or not. I can just say, yeah, I don't know, it might be. Let's find out. Let's do a test. So to do this, remember what I'm going to end up including is a squared component to do a second level polynomial term. So essentially, all I'm going to do is I'm going to make a new part of my data set. I'll call it speed SQ for speed squared. And I'm going to take my car's $speed. I'm going to take that speed column and simply raise it to the second power. And yeah, that's it. Speed squared. There we go. And so now when I run my model, I'll call it polymod 1. I'll give it my distance, that's my outcome variable, squiggle, and then I'll give it speed and speed squared as two different independent variables. And then I'll do summary polymod 1, and this is going to give me some feedback. So again, I don't really, when I look at these terms, and there's a whole complex interpretation of polynomial regression terms that we're kind of skipping. We're essentially saying don't really interpret the terms, focus just on the highest level polynomial in your or highest power in your polynomial. So here, the speed squared, this is my highest one. I'm looking at this. A significant value for speed squared would indicate there is enough evidence to determine that there's a curvilinear relationship. In this case, this is not statistically significant, so we're saying there's not enough evidence to determine a curvilinear relationship. Now, I want you to be a little bit careful, because if you decide to go your own way and not follow Dr. Florin's recommendations, you might accidentally interpret speed and say, oh, there's no linear relationship here either. See, speed squared is that's the curvy part and speed is the linear part. And so you'd come to that conclusion. But that would actually be an erroneous conclusion here. There absolutely is enough evidence to determine a linear relationship. But again, these parameter estimates don't necessarily mean what you think that they mean. So you need to be careful about that. What we're going to do here is I'll just do real quick to demonstrate that there actually is a linear relationship. Let's just pull the squared part out and go back to our regular interpretations. So I'm just going to take the speed squared out. I'll have distance by speed and do that model and run it. In this case, distance by speed, I see that there is a highly statistically significant linear relationship between speed and the distance that it takes to stop. So in our particular case, yeah, there was a linear relationship. Again, when you're studying polynomial terms, really the interpretation, at least for the purposes of this course, just stick to the highest level term. What does this tell you? It tells you, is there a curve or not? And that's what we'll use polynomial terms in this course to test. Now, I will say there is one more way to do this that tries to balance the gap. It does a bit of work with the variables on the back end, and it's the poly term. So if I do poly and then feed it speed, the variable that I'm interested in, and then I give it the degree of polynomial, 2 for squared, 3 for cubed, etc. And then down here at the end, I do data equals cars. This is going to run that same model, and it's going to try to maintain that test of the linear term while doing a test of the quadratic term. Again, the significance now is closer to the significance of our linear term, 1.49 e to the negative 12, 1.21 e to the negative 12. Again, pretty close, but these point estimates are pretty different. So here, again, the terms just don't necessarily mean the same things. That said, this is a quick way. If I wanted to test higher order polynomials, I could say poly 2. Okay, that didn't work. So I'm just going to go back to poly 1. This is the linear term, and then I have that, and my test should be close to matching. Again, be careful of this function. It does some funky work with the variables to try to make the assessments of the different components closer to what they would be if the higher order term wasn't there. But again, in our workflow, I would just ignore this. I would make your squared term, I would run it with all the terms, and then just look at that highest order factor. If it's significant, that's evidence that there's a curvilinear relationship. You can still use this for prediction. That's completely fine. You would just do predict with speed and speed squared as different variables. In fact, maybe we'll close out the polynomial term section here by kind of showing you a fun thing. I actually quite like graphing curves. I think it sounds complicated, and so to me, graphing curves on top of data is just kind of fun. So in this case, let's go on and graph this curve on top of the data set just to see what this looks like. To graph a curve in R, I'll use the curve command, and inside of it, I'm supposed to feed it a function that depends on x. So what I'm going to do is give it my prediction. I'm going to predict based on the first polynomial model I made, and then I'm going to give it new data, and then my data.frame. So all the same stuff, and then speed. But now here, I'm going to give curve x to give for speed. And so it's just going to do all of the different x terms when it makes its curve. It's just going to make a function that has a whole bunch of x terms, and it's going to use the predict function to determine how high the curve should be. So you'll see what happens in a second. So I give it x for speed, and then for speed squared, I'd give it x squared. And is that all I need? Oh, I'm going to do one more thing, and this is just before the last close parentheses. So I'm out of the data frame parentheses. I'm out of the predict parentheses. Now I'm just in the curve parentheses. I'm going to do add equals true. And what add equals true does, add equals true adds this to the current graph. You know, maybe another thing I'll do is I'll do a, I'll just leave it like that. All right, so this is my curvilinear relationship. And actually, I like the way that this fits the data. Now, is there enough evidence to determine at the 95% confidence level that there is a curvilinear relationship in the population? No, but to me, I kind of like this curve. I think it looks pretty good. If I wanted to, I could quickly do the linear model. So maybe I'll call this... well, I'll just do the AB line and then feed it that linear model on here. This is going to add that line. Maybe I'll color it red just so I can see it a little bit more clearly. Okay, I kind of see that. So the linear model, there is a lot of overlap, and it's saying the amount of curvature in the black line, there's not enough evidence in the data to determine that that's significantly different than the red line. I kind of see that, I guess. But it does look like down here, the curve seems to better fit some of these points at kind of the ends. So I actually think I prefer the curve for prediction. I'd want to check the theory, and I don't know enough about physics to know the theory between traveling speed and distance. But if there's some theoretical support, even with a non-significant term in practice, I might keep that. And I do think the curve looks better, even though the statistical test tells me there's not enough evidence to keep it. So if I'm making a claim, I probably don't have enough evidence to support the claim. But just looking at this, I do personally think it works better, even if I don't have enough evidence to make any claims about it. So if somebody challenged me on it, I'd be like, yeah, I see that. Maybe it's not. Maybe there's not a curve there, but I could check out some theory and see, should there be a curve there? All right, so that's my polynomial terms. We are getting close. We just got a couple more things to do. Interactions. Let's talk about interaction terms. I tell you what, let's go back to our marketing data set, marketing. So remember, we had YouTube, Facebook, and newspaper marketing budgets, and then a measure of sales. Recall that if I do interaction terms, and I'm just going to do this poorly, so I'm going to do this incorrectly. So sales, and then I'm going to look at Facebook, or what did I do? YouTube star Facebook. And I'm going to do a summary for this so that I get the significance tests. Oh, and I did something wrong. Oh, I got to give it my data. Data equals marketing. Cool. All right. So what I see is that YouTube is highly significant. Facebook is kind of, it's significant, but not nearly as much as YouTube. And then the interaction between the two is highly significant. So first of all, the interaction between the two is highly significant. That tells me that I probably need to look at an interaction plot as opposed to the main effects. But let's say I forgot and I was accidentally interpreting the main effects anyway. Remember, these effects, that is, I think this one's going to be, move the decimal back 2 places. So 1, 2. YouTube is 0.019. Remember, this is not just after accounting for Facebook. Right now, this is interpreted when Facebook is 0. So if I have 0 Facebook budget, this is the effect of YouTube. And same thing with YouTube. And this decimal goes back 2 places, 0.0288. This is the value with 0 marketing budget placed in YouTube. And remember why this is. When I include the interaction term, and in my notation star, or in R's notation, star, remember, does the main effects of each and the interaction between the two all at the same time. So you're seeing that here. When I include the interaction term, whether it's significant or not, in this case it's significant, so we need to go look at the interaction plot to interpret. But whether it's significant or not, the main effects are now going to change their interpretation. And so I need to be very careful about that. We discussed the process of centering in our lecture notes. So let's talk about what that looks like. Essentially, what that looks like is creating 2 new independent variables. I'm going to call this C_YouTube. It's going to be my first variable. And I'm going to take my YouTube column from marketing and subtract its mean, marketing $YouTube. And I'm going to take the Facebook, make a variable called CFacebook. I'm going to take the Facebook value from marketing, the Facebook column, and then subtract the mean of that column. And these are my new variables that I'm going to include in my regression model. So for my interaction regression model, int mod, I'm going to do that same linear regression that I had before, but now instead of putting YouTube, I'm going to put the centered YouTube variable I just made. Instead of putting Facebook, I'm going to put the centered Facebook variable I just made. Again, check out what you're going to see here. When I run this model, summary, interaction model, what I'm going to see is that the interaction term doesn't change because essentially nothing's been changed there. But what does change is the YouTube and the Facebook values. Previously, and you'll see YouTube more than doubled. Previously, YouTube was being calculated as the impact of YouTube when there was no advertising on Facebook. Now it's being calculated as the impact of YouTube when Facebook is at its average advertising budget. And this is a lot more interpretable of a quantity and a lot more important of a quantity. Facebook, if you're just looking at the number part, looks like it went down. But if you look at the E part, you'll actually see it increased by an order of magnitude. So now we're just looking at 0.18 as opposed to 0.028. So this is almost 10 times higher after accounting for this change in interpretation. Up here, with the interaction term and without centering, this was the interpretation of the impact of Facebook on sales, assuming YouTube was at 0 budget. This is the impact of Facebook on sales, assuming YouTube is at its average budget, which is a much higher impact. So both of these very, very, very meaningfully went up through making sure that we're accounting for this. Again, in this particular situation, because the interaction is significant, we wouldn't interpret the main effects anyway. But I hope you can see through this example where if you don't take that into account, you may interpret values like this, assuming your case there wasn't an interaction or a significant interaction, and make conclusions even though your values should be the ones down here. They can have order of magnitude or more differences. And so it's really, really, really important to account for that. Again, if you include an interaction term in a regression, this is a good thing typically, but when you do that, you have to be careful that you center the variables and interpret them correctly. If I have the interaction term interpreting my main effects, if there's not a significant interaction, now interprets the main effect at the 0 value of the other independent variable. And so that's an important consideration for our interaction effects. All right. Well, let's move on to our next thing, assumptions. So for our assumptions are the exact same as they've always been. I'll plot my interaction model there just to show you. And remember, in the previous simple linear regression video, the assumptions can be found using built-in commands by just putting that into a plot and then doing which equals and then giving it the first two. So I just want the residual plot and the QQ plot. So this is the shorthand way. Interestingly, I can see that there's clearly a pattern in these residuals. So this is a great example of this residual plot where I'm having some clear violations going on here. Essentially, this is a non-linear relationship when I'm looking at it this way. And so something clearly seems to be going on that I'm not taking into account in my analysis in that interaction model. I could then go look at some different plots. I could try to figure out what's going on, but essentially it's the linearity that seems really thrown off here in this plot. All right, looking at normality, again, we see normality is also really thrown off here. I will say, and we didn't talk about this before, often assumptions, I shouldn't say often, assumptions fail together a reasonable amount of time. So different values that say are not normally distributed also may not have the same variance, and that might be a problem. Different values that don't have linearity might have weird normality things going on. What this means in practice is if you do a fix, so if I try to implement a method to fix this assumption for this analysis, I don't just retest the assumption I was trying to fix. I actually retest all of the assumptions, because when I change the data, fixing one assumption might have broken another, or fixing one assumption might have fixed another. So take fixes one at a time and then retest all of the assumptions every time you make a change to see, A, did it fix the assumption you were trying to fix in the first place? And B, if in the process of fixing that assumption, did you fix or break others? The new assumption that we had for multiple linear regression was the variance inflation factor, that is multicollinearity, and that there isn't much multicollinearity. How we calculate that is we use the CAR package. So I can do library. This is already built onto your machine when you download CAR to load that up. And then I will use the VIF function from the CAR package and feed it my model. Oh, MOD, not MAD. Oh, and what am I doing wrong? MOD mod 1. I just want my first model. What did I call it? Oh, this is from a while ago. So why don't I do bin? Oh no, we need one with multiple variables. So let's do our interaction mod, int mod. Now this will look a little weird. Int mod. This will look a little weird and it'll give me a warning because interactions are in the model. And so in this case, it's recommending, hey, maybe just look at these one at a time instead of looking at the interaction term too, because remember, the interaction term is literally multiplying these together. In this case, though, we can see that the VIF scores are very low. Remember, cutoffs are 3 or 5 or 10, depending on who you ask. So values just above 1, well in the range of not worrying about the multicollinearity of the independent variables in this particular case. So VIF looks good, though my residual plot looks terrible. My normality plot looks terrible. Again, remember, we're looking for red flags. This kind of thing is a huge red flag. When remember, this should be an even spread throughout. We're looking for red flags that should be following this dotted line roughly. And this kind of stuff is a pretty big red flag going on here. So we do have some pretty big red flags impacts going on with our assumptions. But, you know, VIF isn't one of them. And yeah, so we're not going to talk about how to fix assumptions. We kind of mentioned a couple of things you could go and Google if you're interested. There are ways to address stuff like this, so don't stress too much about it if that's going on. But you do need to consider addressing it. Again, remember what this would state is our data are very non-normal, and with only a few observations, a couple hundred, our critical values might not be distributed the way we're thinking. That impacts all of our hypothesis tests, all of our p-values, all of our confidence intervals. So all of that stuff can be at risk based on this. Just got to be careful. All right, so the last thing that we talked about, the last thing we'll do in R is standardizing coefficients. Standardized coefficients. So this was when we standardized the x values and standardized the dependent variables. Now, don't get me wrong, you can go and do all of that if you want to. I'll actually go on, I'll create a new model here real quick, just based on the kind of base model for sales that we had to start with, sales, so we don't have to deal with interactions in this YouTube plus Facebook. This is kind of our basic one that we started with, data equals marketing. And I'll call this, I'll just call it mod, whatever. So we can create standardized versions of YouTube, you know, similar to how we did up here. Remember, the scale function is how I standardize a variable. We discussed that in a previous video briefly. So I could use scale and then give it marketing YouTube, and scale and give it at marketing Facebook, and scale, give it marketing sales, save those as 3 new variables, and then rebuild my model and get standardized coefficients. So you can do all that, but R has a package that we can get, install.packages, that kind of does all this for you. It's called lm.beta. So I'm going to go on and install that package on my computer. I'll comment this out because, again, I only need to install it once, and then load it up for use in this R session, LM beta. All right, so here's what I'm going to do. I'm going to look at my coefficients for my previous model, and then I'm going to do lm.beta and give it my coefficients of my model. What you're going to see is it kind of punts on the intercept, and that's okay. What we're looking at is the comparability of YouTube and Facebook. And here we see that YouTube has different values now than Facebook. What do these numbers mean? Well, previously this was as YouTube budget goes up by 1, how much do sales go up? And as Facebook goes up by 1 in whatever units, how much does sales go up in whatever units? In this case, this interpretation for the standardized coefficients is different. This is as the YouTube budget goes up by 1 standard deviation, how many standard deviations do sales go up by? So in this case, YouTube goes up by 1 standard deviation, sales goes up by 3/4 of a standard deviation. As Facebook goes up by 1 standard deviation, sales only goes up by 1/2 a standard deviation. If comparing, we would say YouTube has a bigger influence than sales, not because the dollar for dollar influence is better necessarily, but because as YouTube goes up by a standard deviation in the data set, that has more of an influence than Facebook going up by a standard deviation in the data set. Again, this is an attempt to set 2 different variables which are on different spending scales on the same scale. Now, in this case, because both of these are dollars, this may not make sense to do. The interpretation moving from dollars to standard deviations may or may not be appropriate. But if these were on completely different scales, say this was on a Likert scale out of 5 and this were on a Likert scale out of 10, you might do something like this to say, okay, based on movement around the mean, say 1 standard deviation above, whatever number that is, how does this impact the outcome? And that's where our beta coefficients come into play. All right, ladies and gentlemen, well, that closes out our final R video of our final lecture set for the final topic in this course. Again, thank you so much for sticking with me through this course. It's been a pleasure and an honor. I hope you learned stuff. In this video, we talked about how we can do all sorts of things with multiple regression. We can deal with categorical variables and essentially replicate t-tests, but then add stuff. We can replicate ANOVAs and then add stuff. How do we model curves in R? And then we can actually graph them on top of data, which is kind of fun. We talked about how we can do interactions for continuous variables, making sure we were being careful about the interpretation, because if you include the interaction term, even if it's not significant, the interpretation of those main effects changes unless you center them. And so we talked about how do we center those continuous variables too. Finally, we talked about how we can implement and check assumptions in multiple linear regression, which was identical to simple linear regression, and then how we can do standardized coefficients. And that's something that's probably beyond the scope of this class, but whenever people say, oh, this one's more important than that one in terms of variables, standardized coefficients offers a little bit of a better insight into that than just looking at the raw coefficients. In any case, ladies and gents, thank you again so much for your time. And given that we're at the end of the course, I guess I won't see you in the next video. So I wish you the best of luck on your statistical journeys. And thanks again for joining me in mine.